So my name is Simon Michaux. I'm from Australia. I was educated with a degree in physics and geology and later a PhD in mining engineering explosives. I did most of my work in research and development in Australia, the Australian mining industry. And I worked in the mining industry in multiple sectors. I was collecting information to show that the mining industry was in trouble. In Australia, there were 5 or 6 technical problems that were driving the business model nuts. So, and in 2013, I saw the mining crash 6 months before it happened by attending banking seminars, and I left. And so I left Australia, I left mining, and I came to Europe in Belgium to learn industrial recycling and circular economy. And did that for a couple of years. And then the post in Finland came up for mineral intelligence. And I came to Finland to work for mineral intelligence, which is tracking data patterns in the industrial network from mining and exploration of minerals, but everything that's attached to it: smelting, energy consumption, manufacture, the flows and trades of commodities around the world. So when I first came to Europe in 2015, I used to work in feasibility studies in Australia. That's what I was doing. And when I came to Europe, what I really expected to see was some kind of scoping scale plan. They've been talking about, by that stage, renewable technology for 15 years. And conceptually it hadn't changed. It was still solar panels and wind turbines. But I was expecting, right, this is what we're going to do. This is how we're going to do it. This is, each region will need this installed capacity to generate electricity for these customers. This is who's going to own it, this is who's going to operate it. Or maybe not that detailed, but conceptually, at least how many solar panels are we talking about here? Even at that very, very basic level, there was no plan. There was no numbers, no nothing. There was a distinct lack of hard numbers in any of the discussions, and I saw the most flamboyant bullshit. Yeah, okay, so there were no numbers. And what I found is when I talked to people, you talk to people and the vast amount of money that was being thrown around. Meanwhile, in Australia, the mining industry crashed. People who were doing good work were going to the wall. In Europe, vast amounts of money was being thrown around for almost no results. And when you talk to people, the assumption was someone else has already thought of this, but no one could actually answer basic questions. And it was like a hall of mirrors. So for 6 or 7 years, I thought about how do I communicate what I'm seeing? Because you can't, they weren't interested in hearing the phrase, the emperor has no clothes. So I did an assessment in, the peer-reviewed version was published in 2024. If we were to take the calendar year of 2018, map the world as it was, the entire world, within that world we had Europe, we had China, we had America, and then we had the rest of the world. How many cars were there? If you ask the question, how large was the transport fleet in the global transport? They're talking about electric vehicle batteries. How many cars are there in the global fleet? No one could answer. They could answer for Europe, but they couldn't answer for the entire world. Right, how many cars were there? What classes were there? How many were trucks? How many were passenger cars? How many were commercial vans? What distance did they travel? So, well, why do we care? Well, if you've got to charge a battery, you've got to work out how far does that vehicle travel? What physical work does it do? So we need that. What electricity was generated? How was it generated? Was it coal? Was it gas? Was it oil? Or had all that been replaced, as they say? It turned out no. And what I found was 2 things. First of all, the technology, and so I took each class of vehicle and I replaced it with, say, a diesel truck with a hydrogen fuel cell truck or an electric vehicle truck. And it would do the same physical distance for that class across 1 year based on 2018 data. Therefore, we knew how long it travelled, where it travelled, and then how much energy it would need to replace it. Excuse me. So what I found was two things. First, the task was far, far larger than people had understood, and we'd done maybe 1% of the transport fleet and only 4 or 5% of the power generation. Right, so we had a large hill to climb in front of us. Second, all the existing thinking around the green transition was still based on the idea that they were supported by fossil fuels. All wind and solar plants at the time just generated power whenever, but the base load was fossil fuels. If renewables became the power grid, then they have to be internally self-sufficient. And the problem is they're very, very variable. Now, we saw Spain and Portugal have a blackout a few months ago. Right, that was the variability of the voltages supplied by solar. Wind is also very variable, more so. You need a buffer. Conventional thinking believes only 5 to 7 hours. The sun in summer is stronger than the sun in winter. Logic, right? Right. So what that means is if you're going to supply everything with solar power all year round, you need to balance the difference in winter and summer. And 5 to 7 hours is not enough. Right. I came up with a number of 28.8 days in a simulation I did for Hawaii. To store that amount of power for such a long time, we don't have the technology. Right. So the renewable technology had blind spots. A lot of it wasn't strong enough. It wasn't effective enough for the effort it was to put in its place. Then I actually worked out the metal content in each unit and the number of units, and then summed it all together to work out how much copper, how much vanadium, how much nickel, how much cobalt, how much lithium, and to replace the first generation of units as it was in 2018. And then I put that up against known stated reserves, estimated resources, and estimated resources under the sea, and I found that what we had known in the system we call planet Earth was a fraction of what's needed just to stand still. And at this point, this is a crap plan. We need to go back to the drawing board and do something else. Okay, so I presented this work many times. There were 3 clear reactions. One was shock, that they were unprepared. Second was, even when they're given the time to do so, as in I present more than once to them, they were not able to refute the analysis because I've been using their data. And the third option was they were asking me what they should do. Now, I'm just a guy with a cheap computer and internet connection. I mean, really? But what I actually realised was I was in a unique position where I could do this because I'd done a tour of duty through all energy systems. I was attached to a circular economy division. I did come from a resource sector, the mining engineering, and had engineering and science qualifications. And I had people chasing me with sticks and burning torches saying, fix it, fix it, fix it. Right. So I did a tour of duty through all the systems, and I found that all conventional systems failed. They all failed. They all had some kind of bottleneck. All existing systems that we had running at the moment, like all the fossil fuel systems, also had bottlenecks coming. Something was going to make them fail. So what I did was I put together an unorthodox solution based on 4 or 5 technologies. What's interesting is that they're all about 50 years old or older. And I called it the purple transition. The green transition won't work, but the purple transition might. Why purple? Well, it's my wife's favourite colour. Also, purple's the colour of transformation. Also, when they were talking about colours of hydrogen, there was blue hydrogen, there was pink hydrogen. Purple was the last colour left. So, excuse me. So what I broke this down is, instead of trying to replace the existing system, to actually keep things as they are, turn it all around and says, ask the basic question, what is it we are doing here? What do we want? Why do we have all this stuff? And it says, well, we want to live. So there's the Maslow hierarchy of needs. We want energy. We want transport. We want heat. We want manufacture. We want to deliver our energy in a concentrated form in any part of the world, in any geographic location, in any weather condition, whether it's night, day, whatever. We want to have this to be reliable. We want a low materials footprint. And once we have that low materials footprint, we want each unit to last for a long time. When it does come offline, we want those units to be recyclable. That basic thing doesn't exist at the moment. Wind turbines, for the longest time, and still most of them being commissioned, are not recyclable. We landfill them. I mean, really? All the wind turbines they're putting up in Australia at the moment, there's no plans for decommissioning. They're just going to, I think their plan is to cut the tower down and just leave the foundations buried there indefinitely and move on. And they're doing that in heritage forest. Yeah. So, right. And we also want in our laundry list of what we want to do, our industrial systems have to have a low materials footprint, but a low environmental impact. No waste plume. Not just, like we talk about carbon emissions, but anything industrial has a vast waste plume. Okay. So then we've got the idea that not all energy is the same. Some things, some energy systems serve a different purpose. For example, oil is transport, petroleum. Gas runs our heavy industry. Coal runs our manufacture, and we want the heat. You can't take coal out and put oil in its place, just like it's very difficult to take oil out and put coal in its place. So the new system, whatever it is, will have to have the same basic architecture. So what I came up with was the foundation technology is thorium molten salt reactors. And that's what we were discussing yesterday. It is the decisive point. Reading about thorium and researching it, I found something very interesting, that the existing nuclear industry was trying to lobby it out of existence. When you read documentation, formal documentation from official sources, the language of gaslighting appears. I used to be a professor, and our job every now and then was to assess students, PhD students. How are you going in your project? And we were in a panel, and every now and then you get a student that hadn't done any work, and they're trying to gaslight you into signing the form and letting them live. Right, I saw the same language in these documents. What the difference is the conventional nuclear system is solid fuel. The thorium system's a liquid fuel. It's the phrase liquid fuel fission is the decisively important phrase here. So there is a vast disconnect, and in the documentation look at, anytime you actually sort of looked at how does liquid fuel fission work, what work has been done, what's been assessed, the answer is very little work to no work in the more modern stuff, and they redirect you back to solid fuel. So solid fuel thorium is inefficient. It indeed doesn't work. Or it's not, it might work in the future, but at the moment it's considered inefficient. But the language directs you away from liquid systems like molten salt back to solid, and then it's all over, we're back to uranium. Okay, that's great. So what my point here is this, is there is a vast amount of misunderstanding of what these systems are. In 1972, the Oak Ridge Nuclear Laboratory released a report that showed that this technology did indeed work. It was stable, it could be scaled up, it was economically viable. It was politically killed at the time, and we haven't heard of it since. Now it's starting to break out. The Chinese have multiple systems on the ground, one that they'll publicly admit to, and there's several others that they won't openly admit to, but we'll talk to you about. It's been selling power commercially since 2022. South Korea, the company Samsung is now designing a large natural gas carrier ship with an MSR power source, and that's been commissioned now. There are multiple groups around the world working on this. The most advanced is probably in Copenhagen. The reason I was very enjoyed yesterday's discussion was being in a room full of people who actually understood what this technology was. And the reason that's exciting is it's the only system I see that has any chance at all of addressing the challenges that we face in front of us. I did a calculation on energy return and energy invested for the MSR systems, and the numbers were so high that I had to get someone to check them. So where conventional oil and gas is around, say, 20 to 1, conventional nuclear ranges between, say, 15 to 1 and 50 to 1, depending on who you talk to. Thorium, wind and solar is down around the 3 or 4 to 1. It goes negative if you add batteries. Right, thorium is 1,258 to 1. Now what's driving that is each gram of thorium that then gets transmuted into uranium produces 24 megawatt hours of heat, thermal heat. So it's a vast energy source. Unlike conventional nuclear, thorium can be produced into a working salt fuel very cheaply at any mine site. And the steps are relatively simple. So to make the fuels cheap, the fuel itself is not radioactive. You still have to handle it as a fertile substance, but the hazard sheet says don't get it wet. And that's as far as it goes. The front end and the back end of the thorium systems is orders of magnitude smaller than conventional nuclear. And that's what's driving the very high return. There is, it's very clear, and it's actually relatively easy. The real problem is there's the perception that this doesn't work. It's often been called a conspiracy theory, which is hilarious. The first step is to get a demonstration unit of any size somewhere in the Western world. It doesn't count that it's in China. You know, we can say, oh, they're lying to us. You know, it's a game. If we can get a demonstration system somewhere, like there's a lot of MSR systems that are used in the military, but we're not allowed to access the data. If we could get a system operating, or actually there's already been one. In 2008 there was the Fuji system that was a research unit that ran for 30 years, and they published the results in 2008, and they published the mass balance, and that's what I based my calculations on. And it worked very well. If we could have a publicly seen version that the public could actually observe, and it's actually operating at the moment, step one, somewhere in the Western world, somewhere for you could go and see. You could stand in front of it and have a photograph taken, and then be handed a report of the metrics of performance. Second thing is, once you have that, get information out to the public that this is indeed a real system, and have a comparison between the metrics performance of this system versus everything else. At that point, human nature will take its course. Because all other energy systems are failing. All other planned systems to replace them are facing bottlenecks in delivering on what they promised. Excuse me. So at that point, someone is going to give it a go, and as long as it works, we all give it a go. And it's going to be a sequence like that. And that may well be faster than you think, because necessity is the mother of invention. What's happening in Germany at the moment, when the Russian gas was removed from their marketplace, they had already shut down a lot of nuclear power plants. They'd already shut down coal, and they had no way forward. You said, what do we do? All conventional thinking became a problem. And so now they're going through some very difficult economic years. And until they actually get control of their energy sector, they're going to stay in those economic difficulties. And if a solution is presented to them where they can control the entire value chain of their own energy system and they don't have to talk to anyone else. So I actually went to Copenhagen Atomics and I did a tour of their factory, and I met the people running it, and they are without a doubt the most advanced in the world that I've seen. I stood in front of one of their demonstration. They've got a unit that's ready to go, but it has no fuel in it. Right, but I saw it. I looked inside it. They've got the complexity of, say, a 3-bedroom kit house. I've got a nice photograph in front of one of the test units. So they said they plan to manufacture one of these a day out of that site, and from what I saw, that shouldn't be a problem. They are manufacturing their own fuel. They're getting thorium as a waste product from rare earth element mining in Australia. I could think of a few ways to improve their fuel production around the isolation of lithium-7, but you know, I don't think they would welcome someone from outside the company giving them advice like that. So, but they're very good. They're very good. They have been facing considerable headwinds from a legislative, from an administrative point of view, to get things like licenses to do a test. They could do a test in Africa, but they want to do one here in Europe. So what I believe that they are planning to do is they have a 1 megawatt system, and they will run that system for 12 months. They will monitor it, it'll be monitored, and I hope they're going to publish the blazes out of it. They shout it from the rooftops, here's the data. And yeah, and if that works, then great. And then I think they can sort of get a license to proceed to the next step. But from an engineering point of view, they've been ready to go for some time. So now they need to get our administration, political systems, our administrations, our city councils, and to be comfortable with the idea of a new kind of nuclear technology. And once they're comfortable, then we can look at it. I like the idea of a decentralized power grid where everyone has their own power source. Getting hold of and maintaining the technology is not a problem, it's not that complicated. The fuel is distributed all over the world, which means it's no longer something worth fighting over. So this technology could prevent a third world war. And what I've done is, if I was to do it, if I was to develop it in a city and implement it, that's what I call the Promethean Nexus project. Purple Transition's based on a series of technologies. They are thorium molten salt. We've already discussed that. The combustion of iron powder to replace coal. Now, thorium produces heat at 560 degrees Celsius. We are an industrial society that runs on heat, not electricity, heat. Manufacture, for example, like smelting of metals and everything, you often require up to 1400 degrees Celsius. And so that's quite a jump up. At the moment we burn coal, or the Chinese burn the coal for us. We could burn iron powder and generate 2000 degrees Celsius. Now what's interesting is when you burn pure iron powder, it's not destroyed, it becomes rust. But if you put it in a hydrogen atmosphere or syngas, you strip the oxygen out and you're back to iron powder, or sponge iron. What that means is you've got this industrial fuel that is recycled. You do lose a tiny bit each cycle, but not much. You could take sewage from human society, put it into a pyrolysis plant, which is heating with that oxygen, and 35% by mass turns to syngas. That syngas could then be used to recycle the industrial fuel. So now you've got a waste product from human society, recycling an industrial fuel. That's called a circular economy action. Right, so the next one's pyrolysis, heating things without oxygen. And that's used in several occasions. One of the you get syngas, but you also get like a biochar and a liquid oil, which is suitable to produce fertilizer. Our food production sector has to get off petrochemicals, and regenerative permaculture is the only vector we've got at the moment, and so we need a vast amount of organic fertilizers. That's one side. Next one is batteries powered by something other than lithium, for example, sodium batteries or fluoride batteries for short-range transport, hydrogen fuel cell vehicles and water cell vehicles. I've also got the idea of what I call the spine rail transportation system. When you actually look at the energy, take existing society and take it off fossil fuels and do something else, in the transport sector, trucks are taking the vast amount of the energy. 2% of the transport fleet is taking 40% of the energy, whereas 98%, the cars, are taking about 25%. Right, so trucks are disproportionately taking a lot of energy. What do trucks do? Alice Friedman wrote a book called When Trucks Stop. Okay, so trucks are taking a disproportionate amount of energy. But trucks are also the lifeblood of our society. It's not a case of just stop using trucks. The ability for us to transport cargo from one place to the other. In fact, one of the analyses is when you mineral intelligence is all about finding patterns in data. And the correlation between what's called total liquids consumption, gasoline, diesel, biofuels, whatever, and world GDP is tight. Like everyone in the world all together on the same graph, the raw data unfiltered, R squared of 0.95 or 0.93 or something. That is the highest correlation for any raw material in our sector. So what that means is our modern society, the most important thing to us is transport, moving people and stuff from one place to the other. Not electricity generation, not manufacture, not food production, transport. The implications of that's very interesting. Right, so you look at the transport sector, trucks dominate it. So then I ask the question, what do trucks do? What do they actually do? Well, they're moving cargo from one place to the other. Okay, whether we need that cargo or not is another conversation, but we obviously need to transport it. Is it all the same? Like, do trucks go down all roads the same way? The answer is no. There is a disproportionate number of trucks that would go down a small number of routes between, say, the shipping harbour of, say, Hamburg and, say, a distribution centre. So they would unload shipping containers and they would take them out to a certain place and they'll be unloaded and be a distribution from there. So certain freeways would have heavy truck use, and you often see that. What if we had down those freeways a different way of doing that? So what I'm proposing is to replace some trucks but not all. And what I proposed was the spine rail system, where you have a monorail to shift people on the top, and below that you have a trolley system that would pick up the shipping container and run it along a rail. I saw this concept in Nigeria for a mine site where they wanted to actually move ore from a mine site 80 kilometres out to the coast to a ship. Now, when you put in a rail, it's very expensive. The civil engineering is extraordinary. It has to be just so. But these systems sit up on metal stilts, which means they can go across any terrain at all, and it's relatively cheap and fast. And so if you engineer it where you're going to have high volumes of shipping containers moving down this in an underslung architecture with monorails on top, people on top, cargo on the bottom. Cargo and people now do not interact. You do not have trucks holding up cars, cars holding up trucks. They're moving on exactly the same route. And the whole infrastructure can be powered off the power grid. You do not need fuel, for example, to run this. And I did a calculation for Hawaii. So if you knocked out, say, a third of the cars and half the trucks, then you saved, I think it was like a direct saving of 25% energy for the whole network. And so, okay, so the implication to that, to move cargo around, you now have a rail network. So design your city so you've got a rail network and then collapse everything that you need cargo for to collapse onto that rail line. And that, you see, we're changing the architecture of cities now. The cities, the settlements that are around us now, most of them were put together around the idea of growing crops and moving things with horse and cart and manual labour. So if we start with the idea we have different technologies, how will we design a city around them accordingly? And so this was the Promethean Nexus idea, which is based on Jacques Fresco's Venus project. Right. So I think, did we cover that? Yes. Right. There are a number of other things, but that's the guts of the purple transition. So I've got a number of things. I'm sitting on a technology that helps the extraction of rare earth elements in a way where we don't need dangerous chemicals to do it. It's plasma based. If we were to do that, rare earth elements are not that rare, they're actually all over the world. The problem is only the Chinese are prepared to do what is necessary to extract them, because it's expensive and it's dangerous and it's toxic and all the rest of it. If we used a plasma technology to do that instead, we could treat rare earth elements on the mine site they were mined at. Let's say we've got a mine right here in Norway. Like LKAB, for example, in Sweden, is an iron ore site, and they've got rare earth elements in their feed. The reason I'm interested is thorium and uranium are contaminants that cause a lot of problems. If the contaminants are too high, they're not allowed to transport their ores out of the country. So I'm sitting on a technology that could treat them and then remove the rare earth elements directly with a basic leach step, and the thorium and the uranium at the same time. So if we can actually clean those rare earth elements out, and we're making a thorium stockpile, the rare earth elements are more valuable. What would I like to do? I would like to work with a company that is developing that, and there are a few in America. I would like to, for example, develop my Promethean Nexus project, where I'd have to leave my existing in employment, but then we sort of get capital and funding, and then we would start up with the idea of siting a thorium reactor. The sites I like at the moment are in South America. There is a place right, in fact, the entire, the west coast of South America, it's desert, very little water. And if you are taking seawater from the sea and you put it through a multi-stage flash unit, you're desalinating it to put it through a power plant. You're generating electricity, but on the other side of that power plant, you've got steam that is desalinated. Collect that steam, you've got a vast amount of potable drinking water. The salt, many chemical reactions start with salt, so it's very useful. You could also use the salt in a geopolymer for building materials. Take the salt, use it, and then take some of that energy and get rubber tyres, in particular from mine sites. They have stockpiles of rubber tyres they don't know what to do with. Cut them up, put them into a pyrolysis plant, turn it into diesel. We can make diesel at about 5 cents a litre. So there are lots of options there. But the world's a bit volatile at the moment. It actually makes sense to stay where I am and watch for a bit.